Hi everyone, this is Mr. Cervone. Welcome to my math channel. In today's geometry lesson, we will be learning about what is an inscribed angle. So to get to this, let's first look at the following do now. In a circle with center O, segment AD is a diameter, ABC is a chord, BO equals to 5, and angle ABO is equal to the measure of arc CD, which is equal to 60 degrees. What is the length of segment BC? So how would we solve this particular problem? It seems that at this point, we don't have the knowledge necessary to solve this particular problem, because first we need to know what is an inscribed angle and what relationships exist between chords and inscribed angles. For instance, what is the measure of this angle? Because if we knew the measure of that angle, that would help us to solve this problem. Or, for example, what is the measure of angle ACD over here? Well, let's learn what the relationships of inscribed angles are. But first, let's define the word inscribed angle. So, according to the definition, an inscribed angle is an angle whose vertex is on the circle and whose sides are the chords of the circle. So how does this look like, the inscribed angle? Well, we basically have something like this. As you can see, here we have circle O, then we have two chords, AB and CB, both intersect at point B, and the vertex is on the circle itself. That is called the inscribed angle. And again, in today's lesson, we will be learning about the relationship between chords and inscribed angles, and if there are any relationships also with the diameter of the circle. So let's get started with the first relationship. So let's say that we're given circle O as shown in the figure. We're also given triangle ABC such that the diameter of segment AB corresponds also to the hypotenuse of the triangle ABC. How do we find the measure of angle ACB? And notice that in this case over here, we have this angle over here, which is the inscribed angle. So let me write that in. Inscribed angle. So the goal here is to find the measure of that inscribed angle. Well, this seems a little odd because we don't have any other measurements. We don't know what the measure of angle CAB is or the measure of angle ABC. So how do we find the measure? Well, what we can do here is first construct a segment from O to C. And let's call the angles in terms of X and Y. So again, let's draw segment CO as shown in the figure. Then we'll let measure of angle ACO equal to X and the measure of angle BCO equal to Y. What else can we state here? Well, then we know that segment AO is congruent to segment CO and congruent to segment BO. And we know that because those are the radii of the same circle. And we know that radii of the same circle must be congruent. Notice that now we have isosceles triangles here. So here we know that triangle ACO and triangle BCO are isosceles as shown in the figure, the one colored in yellow and the one colored in green. So now we can say something else here about the angles. Well, then we know that the measure of angle CAO is equal to X and the measure of angle CBO also must be equal to Y. The reason is because if two sides of a triangle are congruent, basically the isosceles triangles here, then the angles opposite those sides must be congruent as well. Now, if we look at the entire triangle ABC, we can now sum up all the angles. Well, we can say that the measure of angle CAO plus measure of angle ACB plus measure of angle ABC must be equal to 180. And we know that because all the interior angles of a triangle sub to 180. Now let's substitute those angles with the values of X and Y. So here we know that X plus Y is equal to 180 by the substitution postulate. And again, notice that the first X value corresponds to the measure of angle CAO, the X plus Y corresponds to measure of angle ACB, and the Y corresponds to measure of angle ABC. And again, they all add up to 180. So basically, here we have 2x plus 2y is equal to 180. And now we can divide 2 on both sides. And here we end up that x plus y is equal to 90. Now notice that x plus y corresponds to which angle here in the figure? It's angle ACB. So this means that the measure of angle ACB is always 90 degrees no matter what. So if we look at this diagram now, we can see x plus y over here. That is 90 degrees. So which means that if we erase all these angles here, so let's erase them really quick. Okay, that means that this angle is always going to be a right angle no matter what, under the condition that the diameter is the hypotenuse of this specific triangle. So this was actually developed by a Greek mathematician a long time ago. His name was Thales, or Thales in Greek. So let's introduce his theorem. So according to Thales' theorem, it states that any angle or opposite the diameter or the hypotenuse inscribed inside a semicircle is a right angle. And again, angle ACB here is an inscribed angle because the vertex touches the circle, and also it's in a semicircle because the diameter of the circle splits the circle into 2 semicircles. But let me demonstrate that Thales' theorem always works. Okay, so again, this is a demonstration that Thales' theorem always works. As you can see here on the left side, we have triangle ABC. C is the inscribed angle, but also angle A and B. Those are also inscribed angles. However, angle C is the one that we want to look at because that's opposite the hypotenuse of the triangle or the diameter of the circle. So at this current location, the measure of angle BCA is 90 degrees. Measure of angle CBA is 24.36 approximately, and measure of angle CAB is at 65.64 degrees approximately. I'm going to click play and see that point is going to move around the circle. See what you notice here with the angles. Okay, so as you can see here, the other 2 angles, basically angle A and B, they do change. But angle C, which is the inscribed angle in the circle opposite the diameter, the hypotenuse of that triangle, is always at 90 degrees, okay? And at this point, we can now go back to our previous do now and maybe think about, okay, how can we solve it? So let me maximize this here. Okay, so if we go back here to the do now, so let me scroll up really quick. So here, now we know what the measure of angle ACD is. So according to Thales' theorem, we know that this is a right angle, okay? So again, how do we solve this problem? Well, we still need to know what this angle here is, right? And it turns out that there is another relationship of an inscribed angle like this when the angle is not opposite of the diameter, but it's opposite of some random chord, okay? So let's look at that relationship. Let's now look at a different type of inscribed angle. Notice that now here, we still have circle O, but now we have the inscribed angle at point A, which is created by 2 chords in which it's not opposite the diameter or the hypotenuse, okay? So let's say that the measure of arc BC is equal to x. Then what is the measure of angle BAC in terms of x? Basically, we want to find a relationship here between the measure of arc BC and the inscribed angle of those intercepted arcs. And just as a side note, when chords intersect an arc, that is called the intercepted arc. So in this particular example, arc BC is the intercepted arc, okay? So again, we want to find the relationship between the inscribed angle at A and its intercepted arc. So let's draw some auxiliary lines here. So first, let's draw segment BO and segment CO. So what can we say about these 2 segments? Well, here we know that those two segments must be congruent because those are radii of the same circle. Well, then we know that the measure of angle BOC is also equal to x because the measure of the central angle is equal to the measure of its intercepted arc. But how do we use this information to figure out the measure of angle BAC in terms of x? Well, we need to draw another auxiliary line now. Well, let's draw a ray that goes from point A through point O and then extend it, okay? Notice that here we're creating two new angles. And let's also call this point over here, point D, okay? So we can refer to it. So we're gonna let measure of angle BOD equals to A and measure of angle COD equals to B as shown in the diagram. So this means that angle A and B, if you sum this up, you get equal to x, okay? So we also know that segment AO must be congruent to segment BO and CO respectively. And I've added it here, okay? And again, because those are all the radii of the same circle. So now we can think about this and say, okay, if you look at angle A or measure of angle BOD, what kind of angle is that compared to triangle ABO? Well, it turns out that that is the exterior angle. And what do we know about the exterior angle of any triangle? That is equal to the sum of each remote interior angle. Okay, so let's write that in. So here we know that measure of angle ABO is equal to measure of angle BAO equals to A over 2. Okay, so there are a few reasons for that. Number one, we know that measure of angle ABO and BAO are equal in measure, or they're congruent, because we know that triangle ABO is an isosceles triangle. And also we know that the measure of the exterior angle, which is angle A, of a triangle is equal to the sum of its remote interior angle. And if they're equal and they sum up to A, then they each have to be equal to A over 2. In a similar manner, we can also say the following about angle B. Let me actually use a different color here. So there you go, I picked red so we can distinguish this better. Okay, so in a similar manner, we can say that the measure of angle ACO equals to measure of angle CAO equals to B over 2. So now let's focus on just measure of angle BAC. Well, here we know that measure of angle BAC, so if we look at this entire angle here, so I'm going to highlight it here. So that is the sum of A over 2 plus B over 2, okay? Which can be simplified into A plus B and then over 2, okay? But notice, what do we know about A plus B? So if we look at this, A plus B is equal to X. So we can actually substitute that into the new fraction that we have here to obtain that the measure of angle BAC is equal to X over 2. And that is actually always going to be the case now. As a matter of fact, it turns out that an inscribed angle is always going to be half of its intercepted arc. So let's look at this and let's develop a theorem now. So the theorem states that an inscribed angle measures 1/2 of the arc that it intercepts. Again, this is the arc that is being intercepted, and if that is x, then the inscribed angle over here must be always half of that. And again, I'm going to show you a quick demonstration that this is always going to be true. Okay, so here's a little demonstration where we can see that it is always true that an inscribed angle measures 1/2 of the arc that it intercepts. Basically the theorem that we have just proven. As you can see here, measure of arc BC is about 72.15 degrees, and the measure of angle BAC is 36.07 degrees, as you can see here. So if we, for example, select one of the points here, let's say point C, and I'll start rotating it around the circle, you can see that both angles, measure of arc BC and measure of angle BAC, will either increase or decrease at the same ratio of 2:1 respectively, okay? For example, if I go all the way here, we can see that this is 67.58 and the measure of arc BC is 135.17, which is exactly in a ratio of 2:1, okay? So this is always going to be true no matter what, okay? That it's always going to be 1/2 of the arc that it intersects, okay? Okay, so now that we have developed both theorems pertaining to inscribed angles, we can definitely solve this problem now. As we learned, measure of angle ACD, that must be equal to 90 degrees. So let me write this here, that the measure of angle ACD, that is equal to 90. And we know that that is true because of Thales' theorem, okay? As a matter of fact, according to Thales' theorem, as we learned, any inscribed angle, any semicircle is always 90 degrees here. Okay, so what can we say about the measure of angle CAD? This angle here. How many degrees is that? Well, if we look at this angle here, and let me highlight the chords here, we have this being the intercepted arc, okay? So this means that the measure of angle CAD is going to be equal to, so let me zoom out a little bit, 1/2 measure of arc CD. So basically we know that the arc CD, which is 60 degrees, so we just simply multiply that by 1/2. So we end up with measure of angle CAD is equal to 30 degrees, okay? So let me label that in the diagram here, so we know that this angle here is 30. Okay, so now if we look at this triangle ABO, so this is 60, this is 30, therefore this angle here must also be a right angle, okay? And we know that because the sum of all angles inside a triangle add up to 180, so if you do 60 plus 30, that is 90, so you're left with another 90-degree angle, okay? And now we can also find this angle here, maybe we need it, angle ADC. So let me write this here, that the measure of angle ADC, that also must be equal to 60 degrees over here, okay? So let me label that one here, 60 degrees. Okay, so here we want to find the measure of segment BC. So how long is this measure here, okay? How do we do that? Well, here we can simply work with 30, 60, 90 triangles, okay? So if we, for example, focus on this triangle here, triangle ABO, we know that the shortest segment, let me zoom in, the shortest segment over here, that is equal to 5, okay? Which means that the hypotenuse is going to be 10 in that particular triangle, and the length from A to O, that must be 5 radical 3, okay? So that is because of the special right triangles rule, the 30, 60, 90 triangles, okay? Okay, so now let's switch focus on the other triangle here, triangle ACD, and you know, that is also going to be a 30, 60, 90 triangle. However, we can say something about segment DO. Well, we know that these are radii of the same circle, they're congruent, so that also must be 5 radical 3. Okay, so now in this triangle, segment AD represents the hypotenuse, and this entire hypotenuse is 10 radical 3, okay? So that means that segment CD over here, so I'm going to write this in here, segment CD has to be half the measure of the hypotenuse in that triangle, okay? So that means that CD is equal to 5 radical 3. Okay, so now that we have CD, which is equal to 5 times radical 3, how do we find the length from A to C, or the length of that segment? Well, we know the relationship of the longer side in a 30, 60, 90 triangle is going to be radical 3 times the shorter segment, or the shorter leg. So basically, we're taking CD, which is 5 radical 3, and multiply that by radical 3. So we end up with the value for AC to be equal to 15, okay? All right, so now we know this entire length is 15. Now, the question was asking us, okay, how do we find BC? So BC is simply equal to 15 minus segment AB, okay, which is equal to 10. So therefore, we end up with a value of BC equal to 5. And that is basically the answer. So we can circle E as our answer. And again, we were able to solve this problem not just because we learned about 30, 60, 90 triangles, but because in this lesson we learned about inscribed angles. And again, the first relationship we learned was about Thales' theorem, that an angle which is opposite the diameter or the hypotenuse inscribed inside a semicircle is a right angle, and also that an inscribed angle measures 1/2 of the arc that it intercepts. Okay, so that's basically it for today's lesson. I hope you enjoyed this lesson. Again, thank you for watching and have a wonderful day.